Physics Challenge 2, Oscillation and Wave. We have the mass m connected to the spring, and the Fick's constant is h or k, sometimes is whichever you like. And what's happened is, if there's no friction here, it keeps oscillating, and the equation is going to be like taking this x. This is the Newton's law. Is going to be k distance. Okay, so k over m equals n square. So we get the oscillation frequency. But if you have a friction, what's happened is we have to know the nature of the friction. Friction force is going to be added on. It's depend on m and says speed x. Okay, so we're talking about damped oscillation. That means oscillations amplitude become less and less over the time. Well, it may not oscillate, depend on how this coefficient relationship is and the mass, right? Okay, so that's what we had to figure out. So this is a case that there's no friction, then frequency is determined by Fick's constant over 4 pi, this equation. Now we're talking about damped. This is a general form of damped oscillation. We have this extra term, okay, and when we have extra term here, for example, the some kind of the friction coefficient and the mass and speed, that's gonna be added in against the Fick's constant x. Okay, so this kind of differential equation, it's just a one-way technique to solve. Is we give a guesstimate function, and here suddenly we change c into a function of time. So we will get this as a solution of this differential equation, but there is the behavior is different depending on how the coefficient worked out. Okay, so our case, mx square plus mu mx plus kx is 0. This is all the force acting on the mass. Total is 0, and this is oscillation with attenuation. Okay, so we divide by m and define the lambda and n square. We will get this solution. So how it look like? It will look like, depend on n is larger than lambda, then it's going to oscillate, but get less and less because of the friction. If n is smaller than lambda, then it's no oscillation, it's just attenuation only, because solution will be containing no sine function, the Triggs function. When n equals lambda, right on certain condition, there is a waveform like this. It's called damped case. Okay, what's happened is it shows single oscillation and attenuate like this. Okay, so for example, if you have a door hanging, and if you open the door, what's happened is the door is going to swing, and friction here is going to slowly stop but you put the damper here, they give a little bit more resistance to the swinging, then it's going to be like this. But if you put too much damper here, door get heavy. If you put too much, it's never swing back and forth. It's going to be just quietly go back, and that makes the door heavy. So this proper amount of damping is the engineering question. For example, you have a car and there is a suspension for the tire, and what's happened is the tire hit the rock, and this is gonna push up, the car go up and come back. It's just keep moving back and forth too long. That's not good. So usually we have a damper attached to it. So what's happened is car goes up, slowly come back nicely. Car sink if it's hit the some kind of hole, but it's come back slowly. So that's the dampers. Depend on the total weight. The damper is adjusted for the car, so it won't go back and forth. If you do suspension by spring only, then you're sitting here and you feel car going back and forth every time it's hit the rock or a hole. Okay, so this is the important parameter, how to come up with proper damping. So one engineering problem is solved. Okay, I hope you like these videos. Please check out the videos, and if you like, subscribe.